Okay. We saw last time that toughness was related to the area under the curve. So we recognize here that the stress for a tension work, we're going back to tensile tests now, was of course force per cross-sectional area. And so thinking about units, we have newtons per meter squared. And we recognize that toughness is reported as the energy it takes to break a unit of volume of the material. So in other words, the area under the curve here better have units that are energy per unit volume. So to help show that, we know that the strain value is unitless. So we'll simply do a little bit more work on the y-axis units to help us there. So our units are Newton per meter squared. I can multiply anything by 1, so I can multiply by meter and have not changed the outcome there. And so the outcome of this is Newton meters per meter cubed. I've achieved the volume information by doing this. And I recognize that Newton times meter looks a lot like force times distance, which is our work equation. So work is equal to force times distance. And the units of work are, of course, joules. And that is a typical unit for energy. So here we see that indeed the area under the stress strain curve does correspond to energy per unit volume by this simple unit analysis. Okay, so why is this important? Well, if we are to try to resist fracture ultimately of a material, it may be that a certain amount of energy for impact on the sample or loading to fracture would occur. So we would want, in service, when materials are in service, to, for example, if we're considering the metal material here, we would want the energy of some condition to not exceed the area represented by the green. So if some condition loaded up this much unit of energy per unit volume, we would recognize that the metal would not fail. And so as an example of this, we'll turn to a YouTube video that's looking at an impact test to absorb the energy due to the projectile onto the canopy of an F-16 fighter jet. And of course, we want that canopy, the window on the canopy, the cockpit window, the curved cockpit window, to not break. And so the energy of the projectile onto that must be dissipated into the structure without exceeding, for example, one of the areas under the curve of these materials. So if it's canopy, if we were using glass, we don't have a lot of area there, but if we're using polymers that are clear for a canopy so that the pilot can see through it, we would need a lot of area under the curve to absorb that energy of the impact. So let's turn to that and see what we see in that video and just how much strain goes into that structure to dissipate that energy from the impact of this projectile. So we'll just turn to that now. Here you can see the canopy in cross-section. Clearly a large structure has hit it, and because the polymer here has a large area under its stress strain curve, we can see that it has been able to absorb that energy per unit volume where the impact occurred, and we've been able to dissipate that energy into the material in the form of heat and other energy dissipative mechanisms. And we have not fractured the material. There's no rupture of the canopy in this case. So test work like this can represent lots of different projectiles, like the sad circumstance when a bird encounters a F-16 jet canopy. Okay, so ductility now. So ductility, we touched on this a moment ago, was the ability for material to be plastically deformed. And so ways of characterizing this there are two kind of main mechanisms. The first is the most common, and so we're going to turn to the failure point for this. And what we do to characterize ductility is we report the percent elongation at failure. Okay, so ductility is going to apply that percent elongation equation, and we're going to use the value at failure and track back to the x-axis for our strain information to help us with the equation. The tracking back, of course, goes parallel to the properties established in the elastic deformation region of the stress strain curve, and so that gives us our x-intercept value, and that's what we use for this piece of the equation. We multiply by 100%, and we get the percent elongation, and that is the a metric for the ductility of the material. For material that has less percent elongation at break, you can see that the ductility would be lower, therefore. And so we've kind of considered these materials before. Ceramics tend to have mostly elastic data in their stress strain curve and very little permanent deformation before failure. So to help us quantify when we can describe something as being brittle, we can use this idea now, this metric of ductility, and say that when the fracture strain of the material is less than 5%, considering this equation here, that the material can be characterized as being brittle. Okay? So if this intercept here is less than the 0.005 value, point 0.05 value, then we would have a brittle material. Okay, your textbook also highlights that for historical reasons, folks would often do fracture analysis. So after fracture, they could measure the new area of the exposed face of the material. So the area, if this were a cylindrical specimen, this area is smaller than it once was, which would be like this. So the necking had reduced the area here, and this new area at failure, AF, is what we use relative to the original specimen's cross-sectional area. And so we take the difference in the two areas and divide that through by the original area, cross-sectional area, and use that for measurement of ductility. So that's more related to fracture analysis on the actual specimen after fracture rather than data points from the stress strain curve. So methods along the lines of approach 1 are the most common these days, but some older work has spoken to the area approach for ductility. Okay, true stress, true strain now. So as you know, the material deforms characterized by things like Poisson's ratio and also necking when we have plastic deformation. And so if we had the ability to monitor the cross-sectional area of the test specimen during the tensional test, if we're doing a stress strain tensile test, we might expect the engineering data, the engineering strain versus the engineering stress versus engineering strain data to differ from what we call the true stress versus true strain curve. So here we just simply modify our definitions for stress and strain slightly, where we're now going to reflect and normalize, for example, in true stress versus the actual area of the test specimen in the moment of the test. Okay, so you see we have an AI. So for every data point I increasing along the test, we have to measure the area. So this can be quite challenging if we don't have any other correlations, but that's the idea. The true strain also reflects the length in the moment, which we were doing already, but we're going to kind of take that in proportion now to the original length. So notice that the numerator here is no longer is a difference, but it's simply the length during measurement minus the original length, and we'll now take the natural log of that to get the true strain value. Okay. So in short, some shortcuts to predict how true stress and true strain are in here, and these only hold if the specimen undergoes no volume change. So for materials that are not yet fully crystallized, there might be crystallization that would contract the material on itself, and this would not be allowed. We would not be allowed to take the shortcut in the box here. So if the material undergoes no volume change under the test work, we can apply these additional approaches. So that is stress as we were calculating it before. So engineering stress is related and transformed into true stress by simply taking engineering stress multiplied by 1 plus the strain value, the classic strain value that we've had. Okay. So again, here, this is simply delta L over L naught. Likewise here. Okay, so our shortcut to calculate true strain is to use that same engineering strain and add 1 and take the natural log of that. Okay, so if there's no volume change, we can take those shortcuts and we can easily transform engineering stress and engineering strain data into true strain and true stress data. Okay.